11.3 example 4 is the integral of 1 over the root of 4x squared plus 1. So you should see if some things apply, like substitution. If you look at a u of 4x squared plus 1 in the regular substitution technique, it doesn't work out. So it turns out there is a substitution, however, that will work. It involves noticing that you're given on the exam 1 formula sheet this integral. This integral has this form where you have an a squared value of 1. This part, however, is a little different. We have x squared here and 4x squared. However, if you do a substitution, you can account for the fact that we have 4x squared instead of x squared. And then we'd be able to just use this result with the substitution technique. So that involves writing our integral in a way that, again, a substitution could be used to use that given integral on the formula sheet. And that would be writing the 2x in parentheses squared, and then the rest of this plus 1 root, and noticing that if you did the substitution of u is equal to 2x, your du is just going to be 2 dx, which is easily taken care of by doing the substitution for dx of du over 2. So you try that. Just write down here that we're just still doing substitution with a different choice of u. What we're going to have is the integral of du over 2 over u squared plus 1 with a root around it. Normally this wouldn't be a helpful substitution, but because we have, again, that given integral on the formula sheet, it turns out it is helpful. Now we have the integral form exactly, right here with their given, except that our u is x and our a is 1 in this formula. So evaluating this integral using the given formula from exam 1 formula sheet would be writing down what we have here, ln, absolute value, but instead of x it's u, so we have u plus root u squared, and then this part is because the plus is on top here and the plus is here. In our problem was plus, this is going to be plus here, and then our a was 1, so this is going to be 1 in here. Close that absolute value, attach your plus c. We just evaluated that integral using that known integral, but we got to put our integral back in terms of x with our u sub. So our u sub was just 2x, so we have ln absolute value 2x plus 2x squared, which is going to be 4x squared, when that 2x is in parentheses, and then this is, oops, I forgot my 1/2 though. Let me put that in there. Forgot it. So now we're done. You could do a bit more simplifying there and with some log algebra, but that's good enough. So this was a really easy problem, it turns out, with just a substitution, but not an obvious substitution, and it involved looking at what we had on our formula sheet. So this is one again of the given integrals that we have. And another thing to mention, if you look on the integration strategy handout, which has got another table on page 3 of given integrals, this one has some stars next to it, and this form of this integral can be derived, or is derived, by using this trig substitution. And it'd be very similar to what we did with what I'll show below. But that's where that actual formula or integration, given integral, comes from. So that's the easiest way to do this. Here is showing the trig substitution method. I didn't bracket it off because I think it's worth looking at. You do have some suggested problems that have sort of this thing where you have a number here, a constant, in front of the x squared part. The form you're given is not quite that, so it shows you how to deal with that. So you can still do that type of problem with trig substitution. So it's worth going through this for that reason, because it would be a similar type of setup, and that might be necessary if there wasn't a shortcut like we just did. So anyway, the form here, if you do this with trig sub, is x squared plus a squared, but again we got like a 2x instead of an x. Your x is equal to a tangent theta, but again recalling that our x is not the x in this form and is actually 2x, you can just correct for that here by putting a 2x is equal to tangent theta where a was 1. So that's how you handle it there. Then you do want to make a substitution for just x, so that involves just dividing by 2, and so you're going to put in a 1/2 tangent theta for all your x's. You find your dx the same way by taking the derivative of that thing and plugging that in. So that is shown here, and then the rest of the problem, or not the rest of the problem, but at least this part is the same as what you're accustomed to without that weird 2x thing and just having the normal x. So you go through the motions here of simplifying using the trig identity, evaluating the integral. The integral of secant of theta is given, so we're just using a different given form integration formula there. So that one is given. And then we have everything in terms of theta, we need it in terms of x. So use that triangle thing. And here's where you have to remember that it wasn't, your substitution for x was not quite that. You can have it in either form, but one form was the 2x equals tangent theta, or the x equals 1/2 tangent theta, either one. And then you're going to play this game, except that, like you normally would, except it's 2x instead of x. So because our a was 1, we just have this made a fraction by dividing by 1, so that we can label the parts in our generic right triangle, find the missing side, and then you can plug in what secant of theta and tangent of theta are with that triangle, and then you're done. So here's the log algebra fancy version, but this is fine. That's it.